Hey, welcome to another episode of Chemistry. Today we're going to talk about redox, defining redox, but most importantly, writing the equations and half equations. So let's define what oxidation and reduction are. Let's try and figure out how to write balanced equations, half equations for redox reactions in basic and acidic conditions, as well as using oxidation numbers to find out redox reactions. Now, what is redox? We've said it a lot. Now, redox comes from two different words. The red part comes from the term reduction, and reduction means you're gaining electrons. The ox part at the end of the word comes from oxidation, and oxidation is talking about the loss of electrons. So you can imagine when we're talking about redox, it's about transfer of electrons. One species is gaining it, one species is losing it. So in another way to represent this, let's just say A is a species and it's got this electron. As part of the process, during the redox reaction, what happens is A loses the electron. And where does it go? Well, it goes over to B. And so in the process, B gains the electron. So how we can describe this is A, oxidation, because it loses an electron, and B, because it gains the electron, it undergoes reduction. To be honest with you, redox, the hardest part of redox is actually sometimes the terminology. That's in my own experience. So we've just spoken about reduction as a process, gaining electrons, oxidation as a process, losing electrons. But now we start using terms like oxidizing agent. Now, when you think about the agent, think that the agent causes the thing to happen. So if it's an oxidizing agent or an oxidant, it causes oxidation. What does it mean to cause oxidation? You're making something lose an electron. You're shaking the other thing to make it lose its electron. So what does it mean? What happens to it, right? If you're making someone lose the electron, well, you're going to take those electrons for yourself, which means that you gain those electrons that you're making the other thing lose. On the flip side, then, if you're talking about the reducing agent, again, the agent causes the reduction. What does that mean? It makes something gain. So it's forcing something else to gain. So essentially what I'm doing, if I'm a reducing agent, I take out electrons from my pocket and I say, please take it. And so that the other thing gains. So if I'm saying, please take it, that means that I am actually losing electrons. See how it's quite confusing? So there's the definition, and I think you call it the noun, where it's the process that's happening, so oxidation, reduction. But as soon as you put the agent, if you go oxidizing agent, the agent causes that process to happen. Let's demonstrate that in our diagram like we did before. A loses electrons, so it undergoes oxidation. But even though it's losing the electrons, we're calling it a reducing agent. Why? I'm losing it to force someone else to gain it. I'm causing someone else to gain it. That's why I'm the reducing agent. B gains electrons, so it undergoes reduction. However, by gaining it, I'm making the other species lose it. And that's why I'm causing oxidation to happen. That's why you call me the oxidizing agent. Okay. And so now that we've gone through the terms and the definitions of things, by the way, I have a feeling that your teacher will probably want to test your ability to understand the terms and the differences between, say, oxidizing agent, reduction, reducing agent. It takes some time at the start to wrap your head around it, but you will get there, I promise. Now, oxidation numbers. This is a tool that you can use to be able to look at any equation and go, I'm sure that's a redox reaction. First things first, oxidation numbers. They're pretty much the charge of the ion. Anything that's a pure element has an oxidation number of 0. Okay. By knowing these numbers, it helps us figure out whether it's a redox reaction or not, and what's been oxidized and what's been reduced. Let's do an example. So let's look at Pb as an ion. Now Pb, as we mentioned, the oxidation number is just its charge, its ion charge. And if it's an element on its own, it has a charge of 0. So you can see here as a reactant, Pb2+, the oxidation number is +2, right? Because it has that charge. But as you go from Pb, you find what happens to it on the other side, it just becomes Pb. Now Pb as an element on its own, it goes to 0. So the question is, how do I go from +2 to 0? Do I gain electrons or do I lose electrons? The first time you do this, it's a little hard for you to wrap your head around because the terms that we use, when you think about gain, you think about it becoming more positive. But in fact, you're gaining electrons, which means you're becoming more negative, right? So by gaining 2 electrons, it's oxidation and the number has decreased. Let me show you. So you start off with +2 and you're adding 2 electrons, which makes your charge to 0. So can you see when you gain electrons, when you are reduced, your oxidation number actually decreases because you're gaining negative charge. You get less and less. This means that lead 2+, so this has undergone reduction. So it was reduced. It's gone from 2+ to 0, which means it gains 2 electrons. Because it's gaining electrons, it's undergoing reduction. Let's look on the flip side. Zinc starts off just by itself as an element. So you can see here it has an oxidation number of 0. But from zinc, it goes from Zn like that to, look, Zn2 plus. So now it's gone to a +2 charge. Now, your number is increased. So what do we think has happened? Zinc has actually had to have lost 2 electrons. Bear with me here. When it loses electrons, your oxidation number actually increases. When you're losing negativity, you're becoming more positive. If you're more mathematically minded, if you start at 0 and you lose, so minus 2 negative charges, that turns into a plus. 0 plus 2 is 2. And that's why the oxidation number increases as losing electrons, because you're losing negativity. And that's why on the flip side, when you're gaining electrons, you become more and more negative because you're gaining negativity. Okay. As a result, we say that zinc has been oxidized. And so what will happen is, in tests and stuff like that, your teacher will probably give you equations and they say, can you tell me which one out of these, multiple choice, A, B, C, or D, which one of these is actually a redox reaction? And you go straight to oxidation numbers. You find out what the species was when it started as a reactant. You go to where it ends up as a product and you just go, what's the difference in oxidation numbers? Is there a difference? Yes or no? And if there is, what is it? And the same thing with here. So you think about what it starts off as a reactant, you go over to your product and see if there's any change that's occurred. Have you gained electrons? Have you lost electrons? By the way, not all reactions are redox reactions. So sometimes you're actually going to find that the oxidation numbers don't even change. And that's when you can say to yourself, well, actually, this is not a redox reaction. Because this is the year 12 version of the redox, the assumption is you can balance really basic half equations, right? So we're going to go to more difficult half equations where it's not just about balancing electrons and charge. Okay, look at this. Let's say you've got MnO4 minus and something's happened in the process and this whole thing has turned into Mn2 plus. The way that I used to explain this to my students is, just imagine you have superpowers. You've got water, you've got hydrogen ions, you've got electrons. Now those are the 3 superpowers that you can use to balance out equations, balance out half reactions, for reactions specifically in acidic conditions, right? So let's think about, as with all balancing of equations, we're just going to look at the elements. So I've got Mn, great, but I've got 4 oxygens here and I've got no oxygens whatsoever in the product side. So I think to myself, I've got an imbalance of oxygens. Then I go, okay, how do I balance oxygens? If I look at the superpowers that I have, I've got water, hydrogen ions, electrons. And the only superpower that I have that allows me to balance out oxygens, because it's the only thing that has oxygens, is water. So what I do here is I add 4 waters to make sure that I introduce those 4 oxygen atoms to balance out both sides. Great, so now my manganese is balanced, my oxygen is balanced, but hang on a second, crap. I've now introduced hydrogen by adding those waters. And so now that I've used the water, I've got 2 superpowers left, hydrogen plus ions or electrons. If I want to balance out the hydrogens, now that there's an imbalance, you've got 8 on this side and nothing on this side. Of course, I'm going to use hydrogen ions. So I go to the reactant side and I go, okay, since there are no hydrogen ions or hydrogens at all on the left-hand side, I'm going to balance it out. And in fact, I'm going to put 8 there. Great. So now I've balanced both the oxygens and the hydrogens. However, by introducing the hydrogens, you see how they're all positively charged? Now I'm pretty much guaranteeing that I've tipped the charges of both sides. So sure, I've got all of the elements balanced. Now the last thing I need to do here is actually balance the charge. So let's have a look here. If we look at the charge on the left-hand side and the reactant side, I've got a -1 charge overall for the manganate, and then I've got 8 positive charges. So overall, I have a charge of +7. On the right-hand side, I've got manganese ions +2, and then water, as you can see, no charges there, neutral. So on the product side, there is a charge of +2. Now, that's an imbalance, and you know that for redox half reactions, you have to make the charges of both sides equal. So the question is, how do I do that? The last superpower that I have here is electrons, and you can imagine electrons will help me balance charge. Now, where am I going to put it? Tip here is you put the electrons where the number is higher. Remember, when we gain electrons, the number gets smaller. And so since you've got +7 here and +2 here, at least you need to put it on the left-hand side. But the question is how many? You can see that I put 5 here. Why? When I do the sum again, +1 + 8 - 5, the total is -2, which is now the same as your product side. So now you have yourself a balanced half equation, a redox half equation in acidic conditions. Okay. When you're balancing these difficult half equations, there's 2 main steps. You balance the elements, then you balance the charge, okay? People like to use the acronym COHET, and they do it in that order. So key elements, then oxygens, you've got to use water for that. Then you balance your hydrogens, got to use the hydrogen ions for that. Make note that that's in acidic conditions. Then they use the electrons to balance out the charge. And finally, making sure that you've got all of the states because it's still a chemical equation. Okay, if you have to balance out half equations in basic conditions, so you can see how I've done the same thing, but let's just pretend that instead of acidic, this says basic. Okay, you notice you do exactly the same as before. Balance out the elements, so using to balance out the oxygens, balance out the hydrogens by adding hydrogen ions, balancing out the charge by using electrons, right? But you notice that because we use hydrogen ions for acidic conditions, there's just a couple of extra steps. Do it as you would normally do it, and then at the end, do this. Add as many hydroxides, because hydroxides use a base or basic conditions, to each side, as many as there are hydrogen ions. So if there are 8 hydrogen ions, you add 8 hydroxide ions, but make sure you do it on both sides. What will happen here is when you have the 8 hydrogen ions and 8 hydroxide ions, they'll come together and make water. So now instead of writing these two, these have become this. You've got an overall net of 8 hydroxide ions on the right-hand side. Then you think to yourself, okay, well, you're almost there, but there are molecules or compounds on both sides that are the same that you can cancel out. So you've got 8 waters here, you've got 4 waters here. Because for chemical equations, we're showing the net change, I don't need to show hydrogens on both sides. I just show the overall change. So instead of going 4, I'm just going to get rid of that 4, and I'm going to say that I've got 4 left here. Okay, so your overall equation, half equation, when it comes to your basic conditions, is what you see below. So really, do the same as what you normally do. Then just add the hydroxides, do the waters, balance it out. There's your final half equation. Okay, now that we've done the half equations and the more difficult ones, now we talk about, well, what do I do when I combine them? What do I do when I've got a half reaction for oxidation and a half reaction for reduction? You balance them. When you do that, you've got to make sure that the electrons for both half equations are the same. Why? So that we can cancel it out. Okay, let's have a look at what this looks like. Let's just say you've got these two half equations, and luckily for us, they're both balanced. But what you notice here is that these two half equations, they've got an imbalance of electrons. Now, that's not cool, because when we write our chemical equations, you'll never see electrons. You don't see them. Okay, you only see them in the half redox reactions, not a full redox reaction. So what we need to do here is we have to think, okay, what do I need to do to make it so that the electrons on both of the half equations are the same, right? Now what you can do here is you can only do multiples. So you can't just all of a sudden add an electron in there because you've got a balanced half equation here. What we're going to do is we're going to multiply that by 2. So what you really have is this, okay? Ag solid. Now can you see how here the 2 electrons, great. So that when I combine everything, they're going to cancel out. And I'm going to show you that right now. So you can see when you combine everything, on the left stays on the left, everything on the right stays on the right, you have the electrons here that you can now cancel out. So your overall redox reaction should look like this. Cool, so that's your final one without the electrons because they've cancelled out. Okay, let's do this. Now, what if I gave you an example like this and I say, no, I'm not even going to give you the half equations, you're going to do it yourself. And then you're going to balance it out. Now, you probably look at this as a typical chemical equation and it's going to be really hard because you can already see that you've got oxygens here, no oxygens here, and how the hell do I just balance it out like that? Great question. So what we want to do first is to pull out the 2 half equations. So find the pairs that belong to each other before and after. So I've got this pair here and I've got another pair here. I'm going to put it on this side. We're going to balance them one by one first, okay? I can see here, that's fine. I've got 1 Fe. The charges are now in balance though, so I'm going to put an electron here. By doing that, the overall charge on the right-hand side is +2 and the overall charge on the left-hand side is also +2. So I'm pretty happy with that. Let's go on this side. Now we've just kind of done that together. So let's much copy what we did before, but let me explain it. 1 Mn, amazing. 4 oxygens, no oxygens. So I'm going to make sure that I can add, do that. Oh, by doing that, I've now introduced hydrogen. So I'm going to balance out the hydrogen ions. I've got 8 hydrogen atoms here. I'm going to balance it out with 8 hydrogens. Now that that's all done, all of the elements are now balanced. The only thing I need to do is to balance the charges. So over here, so far, a net charge of +7. Over here, a net charge of +2. So all I need to do now is to make sure that I add enough electrons to balance it out. So there's 5 here. If I include that, now it becomes +2. Okay, both sides are equal. All right, I'm happy. Both of my half reactions are balanced. Oxidation, so iron 2+ undergoes oxidation to lose 1 electron. Permanganate ions undergo reduction by gaining 5 electrons to form manganese ions and 4 water molecules. Great. Now, if I wanted to put these two together and combine it into a full redox reaction, I'd have to think, okay, now the electrons are imbalanced. I've got 1 here and I've got 5 here. So what I'm going to do is I'm actually going to multiply this by 5. Right? So by doing that, I know that when I combine them together, the electrons will cancel out. That's exactly what I want. So really what that's going to look like is 5 here and 5 here. So if I write everything together, keep everything on the reaction side, everything on the product side, let's do that right now. Cool. So that's what I've got right now. I'm actually going to copy and paste this so I don't have to write it again. Whoop. Okay, so as you can see here, I've got 5 electrons here and 5 electrons there. So I'm going to cancel that out, which means that in my full equation, I'm going to rub that out. Okay, that together and just make sure I finish it off by writing the states. So, cool. That's it. That's how I do it. So start by balancing the half equations first. Then when you put them together, make sure the electrons are the same on both the reduction and oxidation reactions before you combine them for the balanced equation. Okay? If we summarize, we think about oxidation numbers, which is pretty much the charge of the ion. They can help us figure out whether or not something's being oxidized or reduced, and whether or not a reaction is actually a redox reaction. Then when we're balancing equations, just make sure everything's balanced. Elements and charges. So you can use cohes if you want to. In acidic conditions, use the hydrogen ions, but in basic conditions, do exactly what you do for the acidic conditions, but then make sure that you add as many as there are hydrogens to both sides. If you don't add it to both sides, it's not going to work. Cool? Okay. I have a little bonus for you as well. I'm going to show you, and not a lot of teachers will actually show you this, but I will, just in case you want to use it. For some basic redox reactions like this, you can actually get away with not even doing the it out, doing the balanced equation and putting it back in, as long as you cannot use oxidation numbers. And I'll show you what I mean. You can see here oxidation. Let's see what happens here. You've got a +1 charge and you've gone to 0. What that means is Ag plus, so it's Ag plus gains 1 electron. Cool. If we look at Cu, it starts like this. This is the pair. Okay. Starts at 0, then it goes to +2. Now, what has to have happened? Cu actually had to have lost 2 electrons. So you can already see, right, there's an imbalance of the electrons. Remember when we're talking about balancing half equations, and then when you put them together, you've got to make sure the electrons are equal first. You can already see the electrons aren't equal. So what you do is you go, okay, I'm just going to multiply this by 2, right? So I can get the 2 electrons, which means it's just going to look like this, 2 and 2. Pretty cool, right? It works much better when there's simpler ones. When it comes to the ones that involve oxygen, that's a little bit harder, and it's not really something that you're going to be able to do with this as such. Okay, it's not as easy. All right, thank you so much for hanging out with me today. Hopefully those elements were useful and you a little bit more about redox and using oxidation numbers as well as balancing half equations. As always, no matter what anybody says, yeah, you can.